let me throw some stuff I've been working on to you guys. And I'm just trying to see if I make sure I got it. So for example, an agent might be, so we built a bunch of tools around our own finance close process, end of month close, right? So one thing that it does is we have all these credit card transactions that come in. And the job that it does is it looks at all the credit card transactions, look at the GL codes. It even looks at people's calendars to just see what they were doing to figure out, all right, what's the best classification for this expense? And it runs from top to bottom. Sounds like agent, or just a simple, and maybe, I don't know if it's even a loop necessarily. It's just a simple agent loop. What do you guys think?
Yeah, so I would call that an agent, and the main reason is because it's going to run from beginning to end.
Yeah.
And it knows when to start, and it stops when it decides to, and that's it. That's all it does.
Okay. Yeah. All right, now up a level, I have 9 of these different things. We have, what should be invoice, and what categorize those expenses, and what does revenue look like? And there's about 9 of these different things that finance does, all is under this close agent essentially. If I just say, instead of just say go do the ramp thing, I say, hey, close the month, and it runs each of those. Right. Sounds like graph, right?
Yeah.
And maybe that first one is an orchestrator that calls each of the other ones potentially in sequence, maybe in parallel, depends on whether they need the outputs from one to feed into the other. Yep. If it doesn't, then that having nice fan out and being able to do them in parallel will be much faster. So you get some nice savings there. They don't need to actually talk to each other. And then you can take that logic of, did I get the finished and correct output from this agent, move that into your orchestrator, and when all of those are complete, it can call a synthesizer and say, great, here's everything you need to now close the month.
I was just going to say, I think that's going to be the next buzz term, by the way. Like you kind of joked about it earlier, Pete, where we went from like prompt engineering to context engineering to harness engineering to loop engineering to graph engineering.
Yeah.
I think orchestration engineering is a good candidate for an upcoming one.
Next, that's your vote.
In a graph is that there is some orchestration between it, but I think as you make that graph bigger and bigger, all of these orchestration challenges really become such a focus on how do you get that right. And
it's almost like the agent is sort of the individual, the graph is maybe the department, and then there's corporate level. There may be other levels actually, depending on.
Well, and this is where it's interesting, and it's sci-fi, but it's also very real, right? I don't know if you guys remember in 2001, the Space Odyssey, when they sent the guy in to fix the computer. He wasn't an engineer. He was a psychologist, right? Because the AI was broken and they needed to find out why. And I don't think we're too far from that. I think there is a point at which this context engineering or graph engineering or process engineering, I mean, it's management. It's like managing people. The humans are augmented by the machines. The machines are doing some of the tasks by themselves. The whole thing has to get laid out and made to work together in a way that's auditable and improved relative to what you could do with either one alone, right?
So how would you summarize the benefits of this approach? Who wants to take a stab?
Actually, that auditability is a nice one. When you need to give something to a compliance officer and you have that graph, it's a lot easier for them to understand what's happening, because then it becomes like an agentic workflow where here are all of the different steps that happen, and here's how you get from one step to the other. Like what's it looking for to proceed from step 1 to step 2, versus if it's inside an agentic, like just a single agent loop, right? We asked the model to keep going until it got to where it needed to go.
And it did.
It got there. We think.
Yeah, and it's saying the same thing in another thing. It's auditability and predictability as well, right? Like with these agents, when you give them a task, give the same task to Claude Code 5 different times, right? It may reach the same result, but do it 5 different ways, right? And that's kind of, and there's still going to be that inside of each circle in the node, right? But there's more predictability in the lines, if that makes sense.
Well, and it sounds like because you're isolating the job, of that agent, that agent itself should be much more reliable.
Yeah.
Right.
Yeah, I mean, especially if you could sandbox it, right? Really, agents like following the open claw standard and the sort of agents that can write their own content, they're almost like the Marines, right? They just, whatever you got, give them the job, they're going to go get it done, right? But you still need the general telling you where to send the Marines,
Yeah, where to
right?
go.
Otherwise, you could have a lot of stuff going on in a lot of places, right? And so that's really where these benefits come in. And it's interesting because so many of we've been amazed by all the work that the AIs can do, but now that we're getting into the harder, thornier problems, we're getting into the greater needs. And so, a simple example like if you were designing a new employee onboarding, right? You've got to get their business cards printed. You've got to make sure somebody greets them at the door, make sure they go through training, get their I-9 filled out, make sure they're in pay, all those things, right? A lot of those are going to involve a human, maybe verifying documents or a human approving a payroll step. So you can't just say, well, run the agent until it's all done. The agent has to run and go to sleep and wait for an event and then come back alive again. That's not something that an agent by itself does. That's a graph, right? So this graph capability, you might have other cases where you have, within one organization, you have agents need to run in a factory, agents need to run in a data center, and the results of those two need to get brought together. Again, it's a graph. The agents are going to be in one of those places at a time, not in all those places, and they can only sort of reach out and control just to a limited extent. So just the idea that we can have these long running processes that are curated over time, where the process itself is changing and the results are being checked, right? That's the richness that you get out of a graph capability.
I was just gonna say, I didn't hear anybody talk about speed, and if I did, I missed it. Is that a benefit or no?
To the extent that you get repeatability, right? A lot of times repeatability comes from agents through iteration, which then slows things down. So to the extent that a graph is there to say, no, we have a specific way that we know how to do this particular task. That's not an agent. We have this other task that's a little bit more unknown. Let's figure out how to do that part, right? That's definitely an improvement you can get from graphs. The other thing with a that's important when you're assessing the performance of the AI is how much did it cost and how long did it take?
I was just going to come to that. This sounds expensive.
Right. Yeah. Well, I think the reality is in a graph scenario, because it is better defined, you can put a price tag on it. You can say, what is it going to cost to build this? Whereas if you just hand it all to an agent and say, go nuts, right? You don't know how long it's going to take. You don't know what budget it's going to have and the quality of the result that's going to come out, right? So by making those, leave the pieces that need agency in an agent box, but make that box as small as you can. Put those boxes together with a graph that gives you the predictability, the cost control, the reliability, and the testability.
What makes the cost more predictable in that example?
Yeah. So think of it as if you have a task that an agent's going to be asked to do, and 9 times out of 10, it's going to do it consistently the same way. But that 10th time, it's going to go wrong and repeat the task. Well, if you already know how you want it to do the job, don't make an agent do it, because then you're going to have a 10% cost overrun, right? Instead, do it in a way that's prescribed, and that's going to lower your costs. And that effect compounds, because we're not talking about one agent, we're talking about 100 agents that are in these systems, and there'll be massive increases in the cost and the time that comes through. You either have to accept unreliable outputs or you have to accept higher cost. If you want to just stick to that sort of hands-off approach, let the agent do it, you put it into a graph and now it's well defined, the sequence of steps that it's going to go through, the points at which you can measure inside that process, the dashboards that you can get out of it, right? That's what makes it confinable. You can measure it, therefore you can confine it.
I would imagine, though, there's plenty of scenarios, like when you're fanning things out, for example, to have multiple agents do something at the same time, you could significantly drive your expense up.